and show you this in a much more kind of a general way. So the the pattern that actually catalyzed a lot of the attention and the on neutrality was this distribution of abundance, as we call it, where there are two visions of the world. To the right is Sir Ronald Aylmer Fisher, who back in the 40s, he was asked by two insect collectors to help them understand why the collection of butterflies in the South Asia was dominated by rare species. As you can see here, this is the frequency or the number of species, and this is abundance in natural numbers 1, 2, 3, 4, 5. And you see that the largest frequencies, there are a lot of species that are just found with one individual in the sample, what he calls singletons. So he proposed a theory, a very elegant one, that basically say that suppose that the world follows a gamma distribution, and suppose that you sample this gamma distribution following any particular scheme, such as like a binomial sampling or negative binomial way. The interaction between these two things, a gamma and a binomial sampling, generates what he saw, he proved is a log series distribution. And it was very interesting because he made two very important things here. One was that he created what the so-called sampling, a sampling theory, where sampling actually generates the pattern. And he's thought to be the first guy who actually did this. But also, and this is more appealing to physicists, he, especially people working in quantum mechanics, is that he put the observer into the picture. And this is very important because we ecologists usually we think that we observers don't have any telling in what we are seeing, and he made this kind of a very elegant way of putting the observer as part of the co-creation of the pattern. The other guy was also British, but living in the United States. It was Frank William Preston. Preston was well known because he said that pretty much, by he said that the abundance of the species was affected by so many variables that if you invoke the central limit, you will get eventually a normal distribution. But he never was able to find a complete, well, unsymmetric normal, but there was what he called the veil line. And he said, well, this veil line is just something that forbid us to actually capture all the most rare species because we don't sample enough. So he called this a log normal distribution because he graphed all these things in logarithm, and a particular kind of logarithm would call octaves. So the world was either Preston right or either was Fisher right, and for a long time people did this exercise and go there and sample and say, oh, my sample is Preston. Now the other guy said, my sample is not. Preston is more like akin to Fisher. So that was a state of the business until someone who was called Steve Hubble came in and did a unification following the steps a little bit of Moto Kimura, who actually catalyzed what we call the neutral approach in population genetics, saying that most mutations have very slight fitness effects. So in fact, most mutations are neutral. And the importance of a neutral approach is very simple. It is assumed explicitly that the per capita birth and death rates of all entities in a particular community are pretty much equal. The wonderful thing about it is that it allows to do a lot of analytical work, because as I usually said, there is only one way of being equal and an infinite way of being different. So if you are equal, then you can do some analytical work. It's the same thing with working with Markovian versus non-Markovian. There's one way of being Markovian, an infinite way of being non-Markovian. So it's good to do the Markovian model sometimes. So Steve set up to do that, and he came out with this book, 2001, which is the unified neutral theory of biodiversity and biogeography, and that was able to predict a lot of different patterns for this theory, like the relative species abundance, the species-zero relationship, beta diversity, or the decay diversity with distance. And the inspiration he took was from this particular theory, which is the theory of island biogeography. That was set up back in the 60s and 70s by Robert MacArthur and E.O. Wilson. This is the first monograph of this series, and is in the same series at Hubble's, which is one of the great series for theoretical ecology. MacArthur and Wilson, they analyze or try to understand what are the processes that affect the diversity of species found in a particular island. And they set up a theory. Usually the most apparent classical pattern of that theory is what we call the species-zero relationship that nobody really understands very well, but there is this. But behind the theory is this master equation here. So it says, what is the probability P of finding an island with S species? And you have all the transitions. You can have S minus one, and then there was a colonization lambda, or you had S plus one, and there was a death by mu, or you already have S and nothing happened. So interestingly, they never actually did the exercise of solving this and finding if there was an invariant distribution. So what they just did, they did a lot of exercise about the variance, the mean, and so on and so forth, but never actually characterized the distribution. But that was fine. Someone else did it after. This is the equation, and you see here the rates are for species. Well, what Hubble did was exactly the same thing, but let me see how oh, there you go. So he took the same master equation, and now instead of just being rate applied to species, now this rate applies to a particular number of individuals within a species. So he actually set up the equation such that it was the probability of observing k species with n individuals. So what is the probability of observing k species with n individuals? Is that you have k species with n plus one, and there's a death, or there was k species with n minus one, and there was a birth, or there were already n and nothing happened. So then he made the neutral assumption, said, well, let's assume that all our species are demographically identical, so B and K then translate just to be Bn. And dnk is just dn, and you lose the identifier for a species. And he had assumed density independent and so on, and he recovered the log series. That was very interesting. So he found a way of doing this in a way that neutrality provide a glimpse of the theory of and provide a strong support for something that Fisher had developed coming from a different perspective. That was very fun. And then he said, well, if this is the big distribution, as you sample, you get Preston. Perfect. He showed that too. And you say, well, he unified pretty much everything. But there were a couple of problems with this. First, we later on, we realized that someone else has already derived this result back in the 70s. It was a paper, a very nice paper that wasn't really well read. But the most serious one was that he did this, basically. He had a master equation for the number of species within communities, okay? And then he has a master equation for the number of individuals within species. The problem with this is that they cannot be true at the same time, because then if this is true, this cannot be Markovian. Okay, so because the assumption is that all these rates occur at exponential times, and if this is this number of equation for the number of individual is true, then the unless you have only species with one individual, when you have a change in the number of individuals, you will have a change in the number of species. But otherwise, you can have a lot of changes in this number of individuals and no change in the number of species, because then the change in the number of species, which is the first master equation, wouldn't be right, and it will be non-Markovian. So that was a problem. Havel realized that too, but there was nothing they could do about that. Well, one possibility, actually, that we kind of tried to work with was to actually change the frame of reference and do what has been done for ages, which was to go into the diffusion processes, the same as Silverwright did in a very kind of a interesting way. Fisher did too, and there was a big fight between these two guys at some point because of that. And Kolmogorov actually did the theory and showed these guys, this is the way you should do it. And it's in a very kind of elegant way. So, of course, they were working not in the natural number, but in the real numbers, and working with proportions or frequencies, because they were originally working in genetics with the frequency of genes. So the theory that especially Silverwright and Kolmogorov developed was to show that if you have a frequency of a given allele in a total population, which is P, and this population is spatially structured in little kind of subpopulations, the frequency of a given allele in a local population will be actually under mutation and migration, will eventually be described by this invariant distribution here, which is a beta distribution. Okay, so that's what they showed. And interestingly, Kolmogorov, 1935, in this publication here in Russia, he showed that exactly when you have a large population of n individual consisting of S partially population with n individuals each generation k individuals disperse. So it was the same kind of setup that Silverwright had. And then you will have a change that will be described by this variance and means, and you can find using the Kolmogorov-Farber Fokker-Plan equation like this, you will have a solution which is the beta distribution. So he showed in a more elegant way that that was the case using this newly developed techniques. So the beta distribution was the distribution then to describe gene frequencies. So we set up to do the same, changing from numbers to frequencies in a compact support, and working with Rolando Rebolledo, who is a mathematician trained into this school of stochastic processes. And for his dissertation back in 1979, he developed some theorems that allow you to actually work with this distribution using martingales. So what we set up to do was pretty much this. We consider that if you look at the left, we are working with a system that has this dashed kind of contours, meaning that is our main system. But this main system is in interaction with the rest of the environment. And also, there is a lot we might not know about the logics or the dynamics of the main system. And we put everything that we don't know and all this interaction into the noise. So you can actually do a stochastic differential equation like this, where C here is the proportion. Now you have birth and death, and you have this kind of a coefficient of the Brownian here. So the interesting thing is that if you assume that the birth rates and death rates are linear functions, and they do actually, species do not interact, and if you assume a particular form of this C here, which represent is the coefficient, pretty much the coefficient of the noise, so it represents everything that we don't know about the system. You see that this thing can be actually described by this Kolmogorov forward equation, and eventually it will reach out this invariant distribution, which is a beta distribution of this sort. We wrote a paper back in 1976, 77, 1917, actually, not too long ago, and showing that this actually fits very well distribution for different kind of things like birds in Amazon, Lepidoptera, butterflies, and tropical trees and coral reefs. So everything was very, very nice, and especially it actually the real cool thing was that all the alpha and beta kind of parameters here do have a particular way of arranging themselves and do have meaning. Alpha is, we know now, is everything about the factors that allow for the dominance of a particular species, in a particular community. And beta is everything that counterbalance that dominance. And the balance between alpha and beta allows for coexistence, and we now know that they're related to things like migration and extinction rates in ecosystems. This is work we have been doing, trying to test the powerful way of or the biology behind alpha and beta in real meta communities now. So unfortunately, I'm not going to be able to show you that, but so where we are now. So first example was this cultivar of E. coli that through niche construction you achieve neutrality, and now is a generalization of the importance of neutrality, or that species are eventually similar in their fitness for understanding species abundant distributions, and especially the frequency of species in a particular community, and they follow this beta distribution. But we went a little bit further and asked the question, well, was this, even at the beginning of life, can we assume that when life arose in this planet, actually these entities bear the mark of neutrality? So we tried to go back, and the way to go back was to use the most simple mathematical description of a particular entity, which is one way of doing this is work with something which is called replicator dynamics. Replicator dynamics is basically the quintessential way of representing a game theory, evolutionary game theory, where you have a dynamics where things will go into a population as long as they have a growth rate that is higher than the average one in this ensemble that was set up back in the 70s, and derives also from the work. This is very interesting because this replicator equation has been very well worked out. Is also the equation that Eigen and Schuster used for their hypercycle, which was one of the models for the origin of complex life. And also, it has been shown that under appropriate renormalization is also the price equation, the quintessential equation to describe in very general terms the action of selection, and also can be renormalized into the local Terra equation. So this is the replicator equation is kind of the canonical equation. So the challenge with what we did was to being able to work with n replicators to do this stochastic analysis of large numbers of replicators, and we did that, and what we found, as I highlight in the abstract here, is that we show that fitness equivalence does not need to be assumed, but emerges as a condition for the persistence of the system. So the interesting part of this is that we did and showed some theorems for the persistence of the stochastic system here, and to happen, you have to satisfy these neutrality assumptions. I mean, this neutrality thing, and what we have at the end is that the system kind of goes to an invariant distribution, which is the Dirichlet distribution, which is the multidimensional beta distribution. So, what we show in this paper is that neutrality is naturally emerged as a condition for persistence, and that condition for persistence also is reflected in a particular invariant abundant distribution, which is a beta distribution. So that's so far for us. I want to tell you about the principles of this neutrality, and also the importance of niche construction in evolution, and in leading to this neutrality. So we don't really have a theory putting those two things together yet, but it's interesting to think this way. So a related topic I want to talk about now is diversity in time. And I want to point out this because there is much more to neutrality and niche construction. There's also kind of internal dynamics of the systems that might be affecting their own evolution. And if you think of species kind of living in this fitness landscapes that can be very complicated, like the one in the bottom, you think that species somehow have been exploring this fitness landscape and creating all these kind of wonderful forms that we see around. And most of these combinations of genes and phenotype that they express have been gone because they didn't work out at the end. So somehow the world we see is the world that is still being kind of functional. But there is a lot of dynamics of internal dynamics in the system that might affect their own evolution. That this was one of the ideas was crystallized on the work by Perbacks on self-organized criticality. And as you may know, one of the quintessential kind of a toy model was this the existence of these phase transitions when you start building a little kind of a little sand pile, and you keep pouring grain of sand, eventually there will be a critical slope where you will see that avalanches of sand will show up, and those avalanches will follow a particular kind of statistical law, which is a power law distribution of these avalanches. This, as you may know, has been shown in different kind of material, different kind of, interestingly, different kind of rise, and so on and so forth. So there's been a lot of great physics being done in this way. So, but we lacked for a long time ways of understanding what was going on in real ecosystem, and to know if ecosystem actually displays this kind of internally generated or self-organized criticality, so bring itself to this point of criticality. So in the beginning, Kaufman was trying to apply this to the fossil record, and he kind of did this model where he showed that you can claim that this number of extinction events and the size were follow this kind of approximately power law distribution. And Sepkoski also kind of makes some inferences. But back in the 80s, back in the 90s, actually, we realized that there was a particular system that might fit very well with the theoretical expectations. And the system was the Hawaiian archipelago. What happened in the Hawaii archipelago is that it was colonized by the British. And what the British did was, as you see here in the picture to the right, was they kind of settled down in the lower part of the islands. And most of the forest, as you can see here, was restricted to the highlands. Okay, so that's where most of the native species were drew, and looked like British are very fond of birds, of watching birds. So they brought a lot of birds that they usually saw in their kind of backyards in England back to Hawaii, and they introduced that. But the other thing about British is that they keep good track of things, of the things they do. They write down everything, and there was a strong record of introduction of this species. And not only that, but they recorded where, how many they introduced, if the introduction failed or not, and so on and so forth. So, and back in this was written down between 1950 and 1980, and the data was kind of available at some point to analyze. And if you look at what happened is here is to the left, this plot, you have a lot of extinctions, but not until you hit a threshold of 10 species. And if you look at the distribution of the number of extinction events versus the size of these events, they do follow this kind of power law distribution. So for us, this was kind of a nice experimental, I mean, natural experimental way of showing that there might be these critical points where extinction events can happen in real ecosystems, and they will follow this power law distributions. And then Ricard Solé was follow the same kind of or did the same analysis with the fossil record, showing that the distribution of family extinction through time actually followed a particular kind of a spectra that was consistent with this self-organized criticality. But it was later on shown that it didn't. Actually, was shown by John Alroy that in a big compilation that he did, that there was no long-range correlations required for the existence of self-organized criticality. So he said that there was a problem with interpreting this happening in the fossil record. Well, but still, the power law distribution was popping up everywhere within the fossil record. So if it's not self-organized criticality, what might be the actual interpretation of this? And I just came across a couple of friends, Miguel Fuentes, physicist, and Andy Romiger, that was doing a Fulbright stay in my lab. And I put them together and said, well, let's do this, because Miguel was telling me a lot about this thing of superstatistics. and the fluctuations and all the things that it predicted. He has been doing some work on it, and we were interested in the fossil record with Andy. And so we try to put all this together. So the idea behind Superstatistics is a statistical mechanics of different statistical mechanical systems, or many of them. So where you have that if a particle is moving around, it will have a Brownian kind of a fluctuation within each of these, but the fluctuation will have a different beta, which is a different kind of a volatility. And the theory predicts that this particular distribution for the volatilities. And eventually, it might be a way of also getting this power law distribution. So we set out to try to understand if this was going on in the fossil record. And one of the requirements is you have to have the systems that are weakly interacting. So there might not be, so we have to find a way of separating the systems that we are analyzing such that they might fit in this picture of superstatistical mechanics. So basically, we thought that was a picture, each of these peaks was a fitness peak, and we have a particular dynamic within this peak. And we analyzed, for us, the peaks were occupied either by families, order, or phyla of different organisms. So we cross coarse grain the system of these different levels, and eventually we say, well, we will find a level where the interaction between the system will be kind of weak, and we might eventually understand what's going on. So, and eventually the superstatistical description will be great. So the idea was that there was families at some point, or orders will be in one niche, in one kind of a fitness peak, and which actually reflect a particular niche for the species, and that there will be a tendency to stay there, through what we call it niche conservatism. Species through phylogenies tend to keep more or less the same kind of preferences on the same kind of niches, and this is called the niche conservatism. But also there is a force for niche shift and go through this adaptive diversification and exploration of niche space. And now different niches will have these different volatilities or intensities of fluctuation. So we analyze the fossil record. Just to make a long story short, let me show you kind of the dynamic of different kind of families, Lophospiridae and Spondyles, which are sponges and other mollusks. And here you have the cumulative density of how the fluctuation between extinction and origination in each of these families, and this is the composed, and you see that there's a very nice fit to a Brownian kind of fluctuation. And if you look at the fluctuation now of the volatilities, the beta, which are here, you find that as the theory predicted, it follows a gamma distribution. So then with those two things, you can compute the distribution of fluctuations as this integral where you have the distribution fluctuation within an order times, the stationary distribution of inverse variance, or S beta here. And this gives you the prediction for how will be the distribution of fluctuation for the whole system. So, and this prediction was a fat-tail distribution that it worked very well with families. In red is the prediction. This is the cumulative density of the fluctuations. In red is the superstatistical prediction. In blue is the Gaussian. And the dots here are the observed. So the fit is really great for families. It's not that great for orders, and it's really works for classes and phyla. So it looked like families and order really satisfy this thing of being ways of looking at the evolution of life in the last, this is data for the last 500 million years, that you can characterize like working like um, um, satisfying this being kind of a little interactive system in evolution and inhabiting this fitness peak in terms of a particular kind of morphology, of way of life that can be well characterized, like having also this niche invariance and eventually the the exploration of um, different kind of landscape, of different part of the landscape, the fitness landscape. So then let me just stop here because the last part is to consider if the physical environment has any saying here. We we have all these uh, we have all this picture where is the organisms are driven their own evolution through niche construction and in a route to neutrality. Then we have that there's also internal dynamics of the system itself that it might eventually be driven to a particular kind of a criticality state. But then we have to consider the external environment. And the most classical way of looking at this, and I'm just going to show 2 or 3 slides, is temperature. And we not too long ago we did this theory for understanding rate in a very general way, how they are being kind of driven by a theory, which is the Eyring-Ivan Polanyi state transition theory, that give you a way of understanding what is driving traits from metabolism, population dynamics, community dynamics, diversity, abundance. Mostly everything is affected by temperature. And you can do a very nice renormalization of these rates. Not going to go into much detail here, but you can see that there is this data collapse where there is some very universal way of things that are happening here, and we can put all these different you cannot, I don't know if you can read about this, from enzyme activity to energy use, species richness, mortality rate, fecundity for different kind of organisms. And you can apply this to understand a little bit of the dynamics of how fast these rates go. So look like everything else that I told you before might be accelerated by the action of these abiotic drivers such as temperature that might affect how niche construction and the achievement of this beta distribution actually can happen. So with that, I would like to just acknowledge all my friends and collaborators who have been kind of involved in this work through the years. So thank you.
Thank you very much, Pablo, for the very, very nice talk. So we now open the floor for questions, please.
I have a question.
Okay.
Okay, yeah. You have this plot for the beta distribution. You have alpha and beta, and you have a distribution for different groups of species that you try to fit the values of alpha and beta. Yeah. No, it was not this one. Yeah, this one. The values of alpha and beta are very, very different. I mean, alphas are of the order of 1, but betas are very large. Do you have an interpretation for that? I mean, if beta is so large, it implies that the distribution is significant only if x is close to 0, right? That's why you have this peak at 0. But where is that coming from? I mean, it's...
That's a great question because we are right now, I didn't show all the data we have, but alpha and beta, they really, I mean, especially alpha fits colonization rate really great. I mean, if you measure colonization rate in particular ponds, that's what we are working. And if you do it independently, you just measure the number of transition from 0 to 1, and that really, really kind of correlates wonderfully with the alpha parameter. Somehow, also alpha and beta are correlated with the number of species. So if you have either number of species and one parameter, you can predict the other. And you can if you have alpha and beta, you can predict number of species. But we are not yet clear what is fixing the magnitude of these two things. So we're trying to understand the thing, but it really works, and it makes a lot of strong predictions. But the scale still, is escaping. So the other thing is that the beta, and this is the other thing. I mean, we have analyzed the number of families, the proportion of the frequency of gene families within genomes, and it follows a wonderful beta. And if you analyze the alpha and beta parameters, you see bacteria is here, eukarya is here, and plants are here. So it's like different groups have different kind of combination of these parameters.
That's nice.
So yeah, so we are just trying to understand, probably doing a model where we can have more control might be a good thing. But the beta is really, really powerful.
Okay. Thank you.
Now, let me ask you something briefly. You have an inset in that figure that in the vertical goes to much larger.
Right. Well, this is the relationship between the beta, our beta here, the beta parameter, and the parameter that Steve Havel developed for his analysis, which he called the biodiversity number. The biodiversity number is a function of the speciation rate. So we say, well, beta looks like is more related to speciation and actually fits very well with the biodiversity number for this abundant distribution that we fit.
Thank you. So I have Sergio with his hand raised.
Hello, can you hear me?
Yes.
Hi,
yes.
Thank you very much. This is Sergio Pantano, Instituto PoLSAN Montevideo. I have a similar question, but connecting to the last part of your talk. I was wondering, what about the dependence of alpha and beta with the temperature? Because given that they are so different in size, I was just trying to figure out how much they can, I mean, the temperature can affect the behavior of the two parameters, and especially thinking that eventually they go with power laws and everything. So I guess that some of the fitness or the speciation may vary a lot, or some aspects of that may vary a lot with temperature.
Right.
And how do you have a model for that, which I guess is much more complicated?
Yeah, well, thank you for your question. And two things. You mentioned power law, but now it recalled me a fact that when we did the analysis for the gene families, usually people have found power laws distributions of gene families in genomes. And there is a lot of work on that. And the interesting thing is that if either one of these two parameters, as was mentioned by Luis before, goes to near close to 1, this goes to 0 and disappear, and you get a power law. So this is also consistent. A beta distribution is also consistent with a power law distribution. And so that's one point. And the other is that I think it's a great question, because the effect of temperature on the parameters, because there should be a relationship. Because what we are seeing is that most of the dynamics of ecological systems in terms of energy use, abundance, and interaction rates are affected by temperature. So the idea will be, if you rise the temperature, everything will go faster up to some point, and eventually these parameters should change too. That would be my guess, but it will need to be validated at some point. And the good thing is that you can do that with things in very little kind of experiments in the lab. So we are now finishing the other manuscript where we expand on the biological meaning of the alpha and beta and show that it's very powerful. And we hope that people will actually use it to try to understand their own systems. So thank you for your question, Sergio. Actually, you might know the guy who I'm working with is Matias Arin from Uruguay.
Ah, yes, sure. No.
El Mato, yeah.
Okay, thank you very much.
Thank you.
Welcome.
Edgardo Brigatti.
Thank you, Pablo, for the nice presentation. I have just a question. You have presented the Hubble model in its formulation using a master equation. Well, also for the Hubble model, you can construct the relative Fokker-Planck equation going to the continuous limit, and also the corresponding Langevin equation. With this approach, you generate an abundance distribution that has a gamma shape, is a gamma distribution, and in the limit of
Right.
in the limit of vanishing diffusion, you get the Fisher distribution. What relation are between these two theories? The ones that you have
Right.
here with the beta distribution, and the other one that generated the gamma one. Because
Sorry to interrupt, but we are seeing your email, window with your email on top of the
Okay, thank you.
There you are.
So thank you for your question. This is a very fantastic question because there is a relationship and there are many things to be said. One is that if you do the stochastic differential equation for abundances in numbers and you get a gamma, usually if you do it for logistic systems, and that's well known, and that was a wonderful intuition of Fisher saying, you know, if the world is gamma and you sample it this way, you get a log series. So it was amazing. He never showed that the world should be a gamma, but then people have shown repeatedly that the gamma shows up. That's when you work with number of individuals. When you go in frequencies, you should, instead of going to a Fisher, you should go to this one, because that has been kind of shown by things called mographs to these days. And I've been always wondering what happened, and it looked like, and this is some discussion I have had with my friend, the mathematician. You know, he said, usually when they do these large limit approximations, they use Van Kampen. And Van Kampen is great, but there's a lot of Van Kampen that hasn't been kind of formally, analytically shown. There is no theorem, but it works. You know, but there are ways where you can get lost on this route. And the wonderful thing that we did, and that's why it took a long time for us to publish this paper, is that we eventually end up putting a lot of the math in the appendix. But in the appendix there are the theorems that shows that you cannot use any particular birth and death rate in the stochastic differential equation. They have to be linear. If they are not linear, you don't satisfy two theorems that were proven by Rebolledo back in 1979, and you cannot find a particular invariant distribution. If they are linear, you get a beta. If they are not, you get something else. We have never, I mean, the mathematicians working with me on this, they kind of lose interest. That's true. You know, it's like, you know, it becomes like messy. so they lose interest. But there should be a connection, as you mentioned, and the connection which is clear for me is that you have a gamma, and then you work with numbers. Now, look, if you look at the beta, one way to reinterpret the beta is to say, well, the beta is a normalized gamma. You see, so if you transform numbers into proportions, and if the numbers follow a gamma, then you have to normalize the gamma, and then you get the proportion, and then you get the beta and the gamma should talk to each other. How Fisher fits here, I don't know.
But I don't know. When you go to the continuous limit of the Hubble master equation, you are working with frequency,
right?
Obviously, and also this limit has linear growth and death rates,
right?
And you get the gamma. I think I didn't know your nice work. I will go to see more in details, but a big difference is in the noise that you generated. I think that in your model you have an ambiental noise that is linear with the abundance. Instead, if you construct the Fokker-Planck equation and then the Langevin equation from the Hubble model, you get a demographic noise that is a square root of the abundance.
Right. Yeah, right, and that's the right way of doing it, because then you get a square. Yeah. Yeah, I would love to see that. I mean, do you have a particular reference that I can find for that?
Yeah, there is a.
So maybe you can put it in the chat, Edgardo.
Yeah.
Okay.
If you can put it in the chat, that would be great. Thank you.
Great.
Okay.
Thank you.
Okay. Thank you very much.
Thank you.
If sorry, Pablo, if you can put your
right.
your work in the chat. Thank you.
Yes. And it's here in the also in the screen at the top, at the below here.
Okay, thank you.
Thank you. So one last question, Carmel.
Thanks very much. Are you getting me?
Yes.
Okay, thanks very much, Mr. Pablo, and thanks to everyone. I really love the presentation a lot, and it like puzzled me a bit because I had like a question regarding the system globally. Like, do you have a theory or like some models, taking into account the spatial organization of the large community of bacteria already in their maximal amount, capable of coexisting together? Why do I ask this? I ask it because I know this spatial organization may be influenced by, or may have, or may be impacted by the environment. And so I wanted to know if there's already a system that works on this.
Right. Yeah, well, that's a great question, because it would be awesome to have a possibility of working with this into a kind of a spatial arrangement, especially doing some microfluidics, for example, and seeing the evolution of the bacteria. And we know now that the spatial arrangement of patches here might do a huge kind of difference in terms of the coexistence and everything. So, but I haven't seen anyone doing this. But if you follow the first guy who in this paper that we did this with, Juan Keimer, I'm gonna put his name in the chat. Let me see, it's Juan Keimer. He has been doing a lot of microfluidics and specializing, putting this system in space, and it's really, really interesting stuff there. There is no much modeling that you can do analytically, but there is a lot of interesting results they have. And before we go, so thank you for your question. Let me try to find this. for the paper, I mentioned where we do the beta and here it is. Okay, here's the DOI. If anyone is interested in this this article, here it is, and look at the supporting information. That's where the meat is. I hope.
Great.
So thank you very much, Silvina.
No, thank you, Pablo. It was a beautiful talk. I'm sorry that we are sort of running a little late, and I usually very keen trying to keep it on time. But so maybe we can think of trying to organize a school or an activity here at the ICTP-SAIFR where you can come. And so we should try to
that would be great.
Yeah, we should try to advance with something along those lines, I think, also to have a stronger impulse for our network.
Yep.
Okay, great.
Awesome.
So keep in touch. Good. Thanks a lot.
Thank you.
Everybody, and hopefully we see you in a month or so. We have to decide the date though. Bye-bye. Thank you.
Bye.
Thank you. Bye-bye.
Bye.
Bye, everyone. Bye.
Bye-bye.
Bye-bye.